Train mired in snow on platform 1 is the opening lecture by Hélène Hainaut, which is going to be a stellar lecture for two reasons. One, because it's Hélène doing the speaking, and two, because there's that lady over there won't be sitting over there asking questions all the time. So and the talk's title is Relations between the etale and algebraic fundamental group.
Okay, so thank you very much. So I think it's no longer appropriate to thank the organizers, but it is appropriate to thank all of you who got up to arrive here before 9 o'clock, where everything was completely dark. And okay, so nonetheless, I'll deliver my lecture, and let me explain the origin of the conjecture. So if X is defined over the field of complex numbers and is smooth, and if in addition we fix a complex point, then we know that we can define the topological fundamental group. And I'm not going to define it again, and I abbreviate here by top. And there are various completions of this fundamental group. One which is very prominent in the conference, which is a pro-finite completion. And it's more or less the topic of the conference, because according to the Riemann existence theorem, as noticed by Grothendieck, this can be defined purely algebraically. This is the etale fundamental group. So this is the Riemann existence theorem. Which is telling us that the topological finite covering is algebraic if the base is algebraic. And, but there are also completions, and one which is extremely interesting from the motivic viewpoint is the algebraic completion. So let me define the algebraic completion. And the algebraic completion is by definition the pro-system of the H, where H here is a Zariski closure of a complex linear representation. So by the very definition, this is an algebraic group. It's a pro-algebraic group. It's a complex pro-algebraic group. While this one, by the very definition, we can also define it, by the, that's the same thing. That's the pro-system of the H, where H now is by the very definition of the pro-finite completion, this is a pro-system of the H, where H is a finite quotient here. So this one is a topological group. It is endowed with this pro-finite topology. And this one is a complex pro-algebraic group. But I can also think of this pro-finite group here as a pro-algebraic group in a way artificially. As a constant pro-algebraic group over C. And in fact, there is an arrow from the pro-algebraic group to the pro-finite completion by just thinking that if we have a finite covering, it yields a finite local system. And so this arrow here comes from the fact that any H here, which is finite, is embeddable in a GLNC. And in fact, this map is surjective. This is very easy. This is to say that it is surjective is essentially to say that if we have a finite local system, which means that the underlying monodromy is finite, then any sub of this finite local system, sub as a local system, is finite. So this is just saying that this is surjective. And the theorem a very important theorem of Maltsev, which has later on been rediscovered by Grothendieck, and I will give Grothendieck's formulation, is telling us that if gamma happens to be an abstract group of finite type, then we can look at what we just did. We look at the surjective map from the algebraic completion to the finite completion. And if the finite completion is trivial, so is the algebraic completion. So let me now formulate it as Grothendieck did. And in fact, he reproved it for his purpose. So we apply this to gamma, being the topological fundamental group of our complex, the algebraic complex manifold which underlies an algebraic structure here. Then we can say the following. We can say the following. So we can say that if, let us translate, if X has no non-trivial etale covering, then all local systems are trivial. So maybe I should say all complex local systems are trivial, whether finite or not. So it's a quite remarkable consequence. And Grothendieck realized that, in fact, we can formulate this statement here, this fundamental theorem. We can formulate it purely in algebraic terms. So let us do this. So as we know, the pro-finite completion of the topological fundamental group, as I already underlined here, has a purely algebraic definition. So P etale is a purely algebraic invariant. The pro-algebraic completion of the topological fundamental group is also purely algebraic in the following way. In the following way, we know by the Riemann-Hilbert correspondence that there is an equivalence, and in fact an equivalence of tensor category, of rigid abelian C-linear tensor category, so equivalence of tensor rigid abelian C-linear categories between complex local system and vector bundles with an algebraic connection. So in nabla, so algebraic, nabla integrable connection. So it's a tensor category, and consequently, we remember that this group here was a pro-algebraic group, and as a matter of fact, by the very definition, this group here, which we had here, P topologic and the algebraic completion, was precisely, once we think of this complex point here as a neutral fiber functor of the category, this is just the Tanaka group of this category. So this is the automorphism, the tensor automorphism of the fiber functor omega x, where omega x here goes from local system to vector spaces over C, and to assign to a local system here its fiber at a point. But this is still purely topological because we are talking on complex local systems under this infinite, this abstract and topological fundamental group, which has no other structures, no topology, no algebraic structure. But by the Riemann-Hilbert correspondence, then suddenly it becomes the Tanaka group scheme, algebraic group, associated to purely algebraic category. So this is algebraic. So we can think of it as being omega x from the category. So let me denote this by C nabla, from C nabla to the vector spaces, which assigns to E comma nabla the fiber at the point x. And the map itself between, so now we denote this by P algebraic because we gave it a purely algebraic definition. And the map we had, which was also stemming from topology between the algebraic fundamental groups, this complex pro-algebraic group to P etale, the map, and which was surjective here, the map itself here is algebraic. And how can one see this? Basically, as we said before, when we have a finite etale covering here, I mean, we look at the corresponding category of Grothendieck, then we assign to it, I mean, on the categorial side, it goes the other way, and we assign to it the corresponding vector bundle with connection, which is P lower star of OD. And then the theorem of Maltsev, as rediscovered by Grothendieck in this language, is the following one. If, so let me write for short, if P1 etale is 0, is 1, then there are no non-trivial bundles with connections. That means they are all of the shape direct sum from 1 to R. R is the rank of OD. I mean, isomorphic in the category of bundles with connections. And I can go one step further here. I can say, remark, in fact, I should have written it here, I apologize. The category of algebraic bundles with integrable connection is equivalent. In fact, it's not equivalent, it's the same as the category of OX coherent D modules. And we can go one step further. We can also observe, so this as it is written here, it is over C. But now, if we have any characteristic zero field, which is algebraically closed and which is inside of C, then now that we have stated the homomorphism between those two groups here in purely algebraic terms, then this correspondence here carries over to K. So Grothendieck theorem is also valid over K as well. So it raises an immediate question because now we have a homomorphism which is algebraic, which is even defined over a field K. So then we have a K algebraic group here, pro-algebraic group. And one thing I forgot to say is that not only the etale fundamental group is a pro-finite completion of the topological fundamental group, but also by the discussion we had, this etale fundamental group is also the pro-finite completion of the algebraic fundamental group. So it is also its pro-finite completion. So now we are in the position, because everything is algebraic, to raise the question if this is really algebraic, there should be a shadow of this theory here in characteristic P. So what about characteristic P? So as we know, we have at disposal, of course, so X now, and I'm going to have a restriction here. And here, in fact, there is something which is not entirely correct in what I said. I assumed at the very beginning that X was smooth, and the way I presented things here, I was, without saying it, assuming that X was projective as well. And if X is not projective everywhere, I should add here, according to the Lins-Riemann-Hilbert correspondence, regular singular. And then when I said that the category here, regular singular, is equivalent to the category of regular singular or coherent D modules. But the moment I will go to characteristic P, I will assume anyway that X is projective, and you will see why in a moment. So then I don't have these restrictions here, I mean, in mind. So X is projective smooth. Over a field K, so characteristic K is positive. And the theory is a good theory, but we will see later if I have a minute, I will say one word in case K is not perfect. So K has to be assumed to be perfect, but for simplicity in the lecture, I assume K algebraically closed. In fact, the difference is epsilon. It doesn't change much. And so then we have the theory of etale fundamental group at disposal. And what about the algebraic theory? I mean, what about what corresponds in characteristic 0 to the pro-algebraic completion of the topological fundamental group? Well, the moment we have this purely algebraic description here, we can consider the category of all coherent D modules. And this category is highly interesting because we are in, I mean, it works differently than in characteristic 0, but it is a case that this category is also a rigid category. It's a tensor category, and it is abelian, and it is K-linear. That's the main property. That means the harms in the category are finite dimensional K vector spaces. So it's a remarkable property. So if we give ourselves now a K rational point, then we are going to, again, we are going to neutralize this category. So let me denote it again by C nabla. So this rational point here defines for us a neutralization of the category, and we can define the corresponding fundamental group. So we define P1 algebraic of XX to be the tensor automorphism of the fiber functor. And X here, and I just write it like this here. I mean, the X here won't play any role. And this is, so we have this, this group here. And as we had before, we also have, I mean, actually, I can remove the one here. As we had before, we also have a homomorphism. So by definition, it's a pro-algebraic affine, pro-affine K group scheme. And it maps to the etale fundamental group precisely by the same argument we had before to the covering here. We assign the D module, which is again the same one as we had before. This is certainly a D module.
Is pro-algebraic group.
It is pro-algebraic, yeah.
Pi et.
So pi et is Grothendieck's. This is Grothendieck's fundamental group. It can be artificially given a pro-algebraic structure.
Somehow. for unipotent completion?
No. It is, one has to pay attention. This is really Grothendieck's pro-algebraic group. And this is just as before, you can think of it as being those O-coherent D modules which are finite. So you can say, so P etale, it's a profinite over K equals K bar, and any profinite group over K equals K bar is the same as a pro-etale algebraic group. There's no, I don't lose any information. Any profinite group over an algebraically closed field can be thought of as a pro-etale finite algebraic group. I haven't said anything. Now, if I want to relate it to this category, I can say that, and in fact it's a theorem, it corresponds exactly to the subcategory of the O-coherent D modules which have a finite fundamental group. That means if I want to write the, let me write here finite, which would correspond to this map in the sense of the Tanaka formalism, that would be the E, which are D modules, I mean O-coherent D modules, with the property that if I take the false subcategory spanned by it, and its fundamental group with respect to the fiber functor, this is a finite group. Which is obviously etale because, yeah. Okay, is that okay? Okay, so then we have this map, and this map is algebraic. And in fact, so we have this beautiful description. This is abstract, but there is a very concrete description, which is due to Nick Katz. Can you see if I write here, or should I erase there? So Katz says that the category of O-coherent D modules is equivalent to the category of stratified bundle. And what are stratified bundles? Stratified bundles, this is, so we have X, and we look at infinite sequence, so E is an infinite sequence, E0, E1, E2, etc., with the property that the Frobenius pullback, and this is the absolute Frobenius, of E n plus 1 is equivalent to En. So in order to make a K-linear category, in fact, I should give a relative version of this definition, so I don't describe the morphism here, I just describe the object. So that means if you assume E has rank 1, that means all the vector bundles here have rank 1, they are line bundles. What is that? It's a p-divisible group of the Jacobian. It's a p-divisible point. So this corresponds to a p-divisible point of peak X. That means what we are aiming at now, even though it didn't look like this at all at the beginning, is a non-commutative theory which corresponds to p-divisible points in peak. And this is exactly what we are going to do. So we are going to do this geometry here. And immediately, you can raise a conjecture which has been posed by, so conjecture, which has been posed by Giesecker under the influence of Nick Katz more than 30 years ago. And he raised exactly the same question. If P etale is trivial, is it the case that P algebraic is trivial? That means if there are no non-trivial etale coverings of X, is it the case that there are no non-trivial, non-commutative p-divisible points on the scheme? And no non-trivial stratified bundle. This is called stratified bundle here. So it's a very beautiful question. And and the theorem, which is joined with Vikram Mehta, is that this is true. And in fact, much more is true. So I will try to show what more means here, and more is interesting in itself. More is true. And, pardon?
What's the difference between pi and pi 1, or is it the same?
Pi and pi 1. I apologize. Pi and pi 1?
Notation.
Pi 1. I apologize. Yeah, the one, I mean, there are never higher homotopy in the discussion, so I apologize. But this, you're right, this is pi 1. Okay. So that's the problem. And of course, as we all know, if we had a group of finite type which underlied the construction of the etale fundamental group in characteristic P, then we would apply immediately Maltsev and Grothendieck-Sootz. But this is not the case. We know that there is no group of finite type out of which we can reconstruct in one way or in another the etale fundamental group. So one needs a completely different approach to the question. Okay, so let me, you have an eraser here? There should be somewhere in
En dessous de la table, Hélène.
Ah.
Yeah, là-bas.
Ah. In fact, not only one, but
Non, mais
they are all, yeah, exactly. I apologize. Okay. Yeah, maybe I erase here too. So the first thing to observe, so now I will give some aspects of the proof. And so in fact, I will give the Leitfaden of the proof. So the first, the first important point is a theorem which is due to a young mathematician, Dos Santos, who in fact made his PhD here in Cambridge, and this is part of his PhD. He realized, if I express things like this, that as in characteristic 0, the pro-finite completion, I mean, he expressed things in a very different manner, but I express it for our purpose here. If I look at the pro-finite completion of this is precisely the etale fundamental group. So say, maybe I should say this in words, it's more, it's clearer. This means that if one has a stratified object of stratified bundle, the monodromy of which is a finite group scheme, so such that, let me write G as before is finite as a group scheme over K, then this finite group scheme is etale. So it's not difficult, but it's quite enlightening because it gives some support to Grothendieck's conjecture, because it says that, in fact, we are really looking here, the map we are interested in is not only a surjective map, but this map is really the map which is a pro-finite completion. And now let me, so that's, this is, so to speak, philosophically important. It doesn't play any role in the proof, but it's important to know this. And let me indicate, so the proof in rank 1, we will do the proof in rank 1, so assume E has rank 1. And because it has rank 1 for, I don't know, I have to write it L, I apologize. So this is a line bundle. So this is a stratified line bundle, or if you like, it's a P divisible point in peak. And now we know that, in fact, in this case, we just need to assume that the abelian quotient of the fundamental group is trivial, because then we know that the L-addict, so for L, not P, the L-addicted module is going to be trivial. And if the L-addicted module is going to be trivial, then this implies, and now we use really the representability of the peak functor. So I write it because in a higher rank, it's important to know what plays a role here, the representability of peak here. This implies that the quasi-projective scheme peak tau is finite, is zero-dimensional. And as a consequence, if we look, so certainly one should say that if we have a stratified object here, and this will be true in higher rank as well, then the bundles, which is the underlying bundles here of the stratified object, so the underlying line bundles here are algebraically trivial. I mean, they are numerically trivial. So numerically means, and this is a general definition, not only for line bundles, it will mean that for all curves mapping to S, then the degree of those Li on the curves is 0. So they are in peak tau. And as a consequence, because we have only finitely many rational points, because it's a quasi-projective variety which is zero-dimensional, then we have a strictly increasing sequence of indices, so let's say N1, N2, etc., such that Lni is isomorphic to Lni plus 1. Some question?
It's just I couldn't follow why this peak tau is 0. So isn't
because we assume that the abelian part of the fundamental group is trivial.
Problem at P, at the prime P. So the Ti was trivial for L different of P.
Yeah, but it's zero-dimensional. Okay? It's a quasi-projective scheme. It's zero-dimensional, and then those Ni here, because they are strictly increasing, then if you define A to be the difference Ni plus 1 minus Ni, then the Frobenius A Lni is going to be isomorphic to Lni. And consequently, Lni, so this bundle here, for a strictly increasing sequence here, has a property that P to some power A minus 1 is trivial. And because the etale fundamental group is trivial, this trivializes Lni in the whole pro system. So what are the ingredients here? So in higher rank, so let us define the strategy in higher rank. So the strategy in a higher rank is that we are going to use in a crucial way what corresponds to peak here in rank 1, which is a profound theorem of Adrian Langer. And the theorem of Adrian Langer is telling us that he uses a notion due to Simpson. And in the situation where we are going to apply it, I will phrase it directly in the situation where we are going to apply it. If we take a model, so we have X, which is defined over K, and we take a smooth projective model, XS over S, where S here is, let's say, affine, smooth over some finite field, then he says that the functor, so the functor M relative to S of, I just write vaguely here, of pure sheaves. So pure means that they have a pure support. Of pure sheaves which are Gieseker stable. On fibers, on geometric fibers. Is universally co-representable. By a quasi-projective scheme, so S scheme, MS. So it doesn't say that this is a fine moduli functor, but it says first that it is quasi-projective, and it says in particular that if we make the best change here to K, then it will be MK. And if we make the best change here to a close point, then it will be MS. XS, excuse me. Yeah, I come to this, thank you. And Gieseker stable says it's a slightly looser stability notion than the standard one, but it includes the standard one. So there's one information here I forgot to give, is that because X is projective, I have a polarization. I give myself a polarization for the discussion here. So we have X. So it's a relative polarization here. And we have the notion due to Mumford of mu stability, which means that the degree, so for a vector bundle, I just write it for a vector bundle, which means that the degree of E with respect to the polarization divided by the rank here fulfills the stability condition. So it's strictly decreasing for subbundles. And Gieseker, so usually it's called chi stability. It says that the stability condition is not going to be fulfilled for this function, but for the Hilbert polynomial. Chi E of n, which by definition, or I apologize, P E of n, which by definition is chi of x E twisted over OX with OXN divided by the rank here R of E. And there is a chain of implication, but one implication is that mu stable implies chi stable, and in fact implies chi unstable, which implies mu unstable, but we won't use this.
What means that the Hilbert polynomial is stable?
Pardon?
What means that the Hilbert polynomial is stable?
It means the same thing, that it satisfies the stability conditions. This means for any, let's say, E1 in E, then the Hilbert polynomial of E1 is strictly smaller than the Hilbert polynomial of E, where strictly smaller means that the growth of this polynomial as n goes to infinity. Yeah, excuse me.
Maybe you want to say for any E1 and E2.
Pardon? So E is stable if and only for any sub-object, its Hilbert polynomial is strictly lower than the Hilbert polynomial.
But what about 2? E1 contained in E2, it doesn't have to be.
2? What is
Don't
2?
you ask?
No.
The stability condition means that actually the slope always is zero, but the point is not you just take 1.
For stability
What?
of E1, I guess.
Yes, what happens if you...
No, I don't say anything about E1. E is stable if and only if all its sub-objects have the property that their Hilbert polynomial is strictly lower than the Hilbert polynomial of E.
My question was, what about if E1 is contained in E2,
Yeah,
sub-bundles of E?
yeah.
Don't say that.
No. I certainly don't say that. Okay, because at the end, it doesn't say that this E1 is going to be a point of the moduli. It just says that in order to have this as a point of the moduli, you need that all possible sub-bundles in the category of bundles do fulfill this property. Okay? Okay, so then we have those moduli. That's number 1. And now comes the second thing is that if we think of peak, what plays a role here is the properties that we look at on peak. And in fact, observe, so here, and we make the next remark, which I made already earlier, is that such bundles here which are stratified, so if E is a stratified bundle, then all the EI are algebraically, numerically trivial. And in fact, this is, if in fact even more is true, it is also true that all the Chern classes are numerically trivial because we can write like this because all Chern classes are infinitely divisible, infinitely p divisible. So this means that such a stratified object has a property that if I look at their Hilbert polynomials for all the underlying bundles here, they are just the same as the Hilbert polynomials of O here. And so then we have moduli. So we have those quasi-projective moduli. Here I forgot to say, I apologize, that the functor of Langer is telling us that there is this quasi-projective scheme. So Giesecker stable with fixed, I apologize here, with fixed Hilbert polynomial. And the one I choose, of course, is the one PO. I apologize. So now, what plays a role here, obviously, is the fact, by the very definition, that we would like, so we would like to think we would like to say that all the underlying vector bundle here define moduli points in the moduli. And, but this is not true like this, but we will see how to overcome this difficulty. And we would like to say that, in fact, we are going to work on the moduli, and we are going to look at what corresponds to, so let me write below here, when we are on peak 0, and we look at the operator which to a line bundle here assigns its piece power, I mean the Frobenius pullback, we know that this is, it corresponds, if I just think of the abelian variety as an abelian variety, it's called the Verschiebung. That means if I think of it on points, this is a Verschiebung. So we would like to define here a Verschiebung on M. And the Verschiebung should have this property that to a moduli point here, E, we assign the absolute Frobenius pullback of E. But the problem, as already discovered by the Giesecker around the same time, is that even if E is stable, then it is not the case, not always the case, that its Frobenius pullback is stable. That means this Verschiebung operator on the moduli it's not defined. Not everywhere defined. So let me indicate how to overcome those two difficulties here. And then give the main idea of the proof. So the first difficulty here, which is much easier, there is an answer which is a little bit suggested in an article by Brenner and Caid. I think Caid here is here in Britain, where they observe that if we have a stratified bundle like this, it is a case that if we go deep, deep, deep in the stratified bundle, so for n large enough, the En is going to be semi-stable. And what is true is the following proposition. So it's not there, but somehow it's more or less, their article gives this kind of idea, is that any stratified object, then there is an N0, let's say, such that the shifted stratified object which starts with N0 plus 1, etc., has the property that as a stratified object, it is a successive extension of stratified object, let's say, of the shape U, U0, U1, etc., where all Ui are mu-stable. That means in order to prove the Giesecker conjecture, if we can deal with such E0, E1, etc., with the property that all EI are mu-stable, then what we need to conclude is the following lemma or little proposition, and that's the only place where the categorical viewpoint plays a role. Namely that if the pro-p abelian is 1, so it's much less, it's still only the abelian part which plays a role here, then there are no non-trivial extensions. Of the trivial stratified object by itself is 0. And do I have? I can just indicate this is not difficult. The point here, let me just write the point here. And again, this is in the thesis of Dos Santos. I mean, it's not expressed like this, but that one can easily compute the X1 stratified. This is just the pro-system here over the Frobenius on H1O. And, but because we are over an algebraically closed field, in particular over perfect field, then we have a splitting, as we know, from the etale part plus the nilpotent part. And by our assumption, this part is 0, and the nilpotent part here is finite dimensional, so there is a fixed power of Frobenius which is going to kill it, and consequently it kills the pro-system here. So now we are in the core of the problem, and we come to the main difficulty, and the main idea is the following. So the main definition is the following. We define for any closed subvariety, and subvariety, that means we look in the reduced subscheme here. So for any, if n is a closed subvariety, we say that n is Verschiebung divisible. If the Verschiebung which we defined earlier on, that means from the Verschiebung restricted to n, which was not always defined, we define it on points. So for any moduli point here, we assign the Frobenius pullback. So we say it is Verschiebung divisible if V is a rational map. So if, so maybe I should say V from M here. If V restricted to N is a rational dominant map from V to itself. Thank you very much. I apologize. From N to itself. So we define this notion of Verschiebung divisible, and why do we do this? Because we observe, so then define one example of such N, define N to be the Zariski closure of all the En, where E is a stratified bundle here, where all the Ci, as we said before, they are moduli point. And then this N is Verschiebung divisible. So once we have the main definition, we come to the main tool. What we do is because we are free to move, so we take a model which will have the S will have the property that the N also has a good model. and N has a good model, will mean in particular that all the irreducible component of N will be defined over S. So N is Verschiebung divisible. Of course, it's a theorem that it's Verschiebung divisible. So all the irreducible component will be defined over S. And so then the Verschiebung is going to permute those components because it is Verschiebung divisible. So some fixed power is going to fix the components. And then we go to a close point. And then some, again, those components, this one component, maybe it might break into several components, and we go again to a finite covering in such a way that all are defined over the close point. So such that a component of this one component we took here, restricted to S, are again defined over S. And then we can again erase, so then the theory of Langer is going to imply that we have a compatibility from Vs. So then the model here was such that V had also a model, so Vs, so S is a close point, with a Verschiebung at the close point. So then we are in the situation that we have a scheme over a finite field with a rational map, self-rational map, which is dominant. And then we apply the theorem of Hrušovský. So we get out from algebraic geometry and go to the theory of models. So we apply the theorem of Hrušovský. Which says that if Y is an affine algebraic variety over FQ, which is geometrically irreducible, and if gamma is a graph in the product, so this Y is going to be a non-trivial affine in the component I'm looking at, in component over S, on which this power of Frobenius, this power of the Verschiebung here, this large power, let's say M, is an endo. I mean, it's a rational dominant self-map. So then gamma is going to be the closure of the graph. And then Hrušovský is telling us that whenever I have a gamma here, which is absolutely irreducible, and which is dominant on both sides, then and if phi q, I write in order to distinguish, I write by phi lower fq the Frobenius of Y defined over fq, then for any closed subscheme, subvariety here, then there will be an let's say an n, a natural number, and there will be a close point away of Z with the property that U phi fq n of U lies on the graph. And if one thinks a little bit, if one takes Z to contain the indeterminacy locus of the power of the Verschiebung we are looking at, and gamma to be the closure of the graph, with a little bit of some slightly more thought here, one deduces from it that we will find a use for any these. There will be a U here, a close point in the moduli, in S, with the property that the Frobenius pullback on X, S, to some power, let's say n, is U as a moduli point. So this shows, and this is what I said before, and I want to formulate this theorem as a separate theorem here, but I express it in a quite lax way for lack of time here. This shows the following. So that's, so to speak, the general theorem, which has nothing to do with the assumption on the fundamental group. That if we take n in M Verschiebung divisible, n is a good model, then the torsion point in this sense are dense. And torsion point here refers to the fact that we have a close point of NS, so a U close on NS, so it maps to a close point here, and on S, there is some power here. And now, I just take 1 minute to finish the proof. Now we apply a theorem, a very beautiful old theorem of Lange, Herbert Lange, and Stuhler, who showed that a vector bundle, if U was a point in peak, this would be a Kummer equation. This would mean a power of a line bundle of degree prime 2p is trivial. So that defines the Kummer extension. And the theorem of Langer and Stuhler is an extremely beautiful non-commutative Kummer generalization of this. So this says that if E is any vector bundle with the property that some power of Frobenius is isomorphic to E as a vector bundle, then there will be a non-commutative Kummer extension, let's say H, Y, so this is etale and finite, which trivializes the bundle. So now we can conclude, because, and I finish the proof, we apply the main theorem here. If we assume now that Grothendieck's fundamental group is trivial on X, then because we have a good model, it will imply that the specialization map is surjective. So then the Grothendieck fundamental group on the close point and then its algebraic closure is trivial. And as a consequence, this H of Lange and Stuhler is trivial. And this is a contradiction because we have a stable bundle. So I apologize for being over time. So thank you very much.
Questions?
So I can, yeah, I apologize.
Okay, so what happens if you just try, very simple-minded, you have a projective motority over a finite field?
It's not finite field, that's the main point.
Characteristic P.
Yeah,
Algebraic.
okay, yeah.
And you lift it to a variety over algebraic closure of the bit vectors.
Yeah, so this was the first thought, and in fact, thank you for the question. It's an interesting question, and it brings me to two directions. So the first one is that this was my first try, and I had gone quite far discussing with Yves André, because the thought was, let us simply assume that the scheme lives, the variety lives. Of course, it's not general, but it doesn't matter. And we can try. And because of Santos' theorem, which is slightly more general than what I said that the pro-finite completion of the algebraic fundamental group is smooth, is etale, is pro-etale, so it's smooth. He says more. He says that any single group in the pro system is smooth as well. So it's a very natural thought to think that we can try to generalize Grothendieck's fundamental theorem, exactly the one I use on the specialization here, for smooth but not finite group schemes. And, but we could not do this, but I had gone further because I had computed with other ideas of Grothendieck that if we were able to do that, in fact that's the reason why Yves suddenly thought like this. I had computed that if we had been able to do this, then with some work we had a chance to apply other arguments which are more or less due to Grothendieck to finish the proof. But the point is that we cannot lift. I cannot give you a counterexample, but I'm not able to lift a stratification. And in fact, Dos Santos, meanwhile, has a preprint where he gives some conditions under which one can lift a stratification. And those are so strong that, so that means you need the scheme to lift, and then you need the stratification to lift, and okay. So it doesn't work. I mean, at least in the present state of knowledge, it doesn't work, but this was the first thought, and this, of course, would have avoided the use of a model theory here. But it brings me to another thing, is that Michel Reynaud read with extreme care our manuscript, and this was very nice because he asked 1,000 questions. And then he formulated a conjecture, or a question, let's say, but slightly more than a question. He said that now assume we are in the situation, which is completely inspired by the method, even though I had no time to go into details. He said, assume now we have a relative stratified bundle. I didn't define the notion of relative stratified bundle, I just defined the notion of an absolute stratified bundle. The relative stratified bundle would be relative D modules, which is all coherent. This means that this infinite sequence of vector bundles defined by cats would not live on the same variety. I mean, you would have x, x1, x2, everything over k, with a relative Frobenius, and you would have an infinite sequence of vector bundles which corresponds. That means you are not in one moduli. You are each vector bundle is in a different moduli, and then you have a Verschiebung between the moduli, just like the standard Verschiebung on peaks, the genuine one, and that's the one I had written. And then he says that if S here is defined over, so now assume that you have a relative situation and K is a finite type over Fp, then it should be the case that this object is finite. That means its Tanaka group is finite. And if this was true, we cannot prove this, even though Michel made some attempt, even in rank 1, some progress, but it's not done. And if this was true, this would be a perfect analogy to the P curvature conjecture of Grothendieck, because the P curvature of conjecture of Grothendieck starts with a connection in so D module connection characteristic 0, so relative to C, or relative to a field of characteristic 0, and then so makes it over, as usual, over a ring of finite type over Z. It goes to characteristic P, assumes, I mean, he assumes even less, he just assumes the P curvature is 0. And there he wants to say that this implies that the monodromy over the algebraic closure of the original field was 0, is finite, and this is a absolutely one-to-one analogy in equal characteristic P. And so then the thought is that maybe those methods yield to this, but so far they don't do. And I should say that Yves André earlier on has an extremely beautiful article where he shows the equal characteristic 0 analog of the P curvature conjecture in characteristic 0.
But can you suppose this if you have such the picture at the top? You already can break it down to something of finite type over Fp is not clear.
No. What I say is that this is the assumption we had here that we are looking at absolute stratified, we are over an algebraically closed field. And then, of course, over an algebraically closed field, we have many stratified bundles which are not finite because we have, for example, the commutative set, we have p-divisible points. So there's no point because the field is algebraically closed, okay? But the moment your field is a finite tap over FP, then it's not the case because you have Néron long. So whatever you do, you will stop at some point. But this is the absolute version. So and now, if you like, you want a Néron long, a relative Néron long. That means you don't assume that you have a p-divisible point, but you assume that you have a Verschiebung divisible point in P, and you want to see that this one is torsion. And even that is not clear right now. And that would be really the equal characteristic P analog, a rank 1 analog of Grothendieck section conjecture, going from characteristic 0 to characteristic P.
Great.
Yeah, apologize. And thank you very much for getting up in spite of all the adversity. Yeah.
Great. So other questions will have to wait until coffee time because we're about to start it again. So thank you very much, Helen.